Okay. It's a pleasure to introduce today's speakers, which is Celia Anteniodo. She's a professor of physics at the Pontificia University in Rio since 2004. She has a degree in physics from Buenos Aires, Argentina, actually, and a degree in physics from the Brazilian Center for Physics Research. You find the CV in the internet, and then you find out interesting things. Like she has the PhD in experimental biophysics. It's been a long way since your beginnings to here. She did part of her thesis in Waterloo, Canada. Then she did postdoctoral research in nonlinear statistical physics at the Biophysics Institute of the Federal Institute of Rio de Janeiro. She was there for 4 years, from 1997 to 2001. She has been, among other things, a member of the editorial board of Physical Review and co-editor of the Physics Letters. And her current interests are in statistical nonlinear physics, and including stochastic dynamics, nonlinear dynamics, and emerging collective properties of complex systems. Although today she's going to talk about something apparently different, which is this minimalist thermal diode. Thank you.
Thank you. Thank you very much for all of you being here. This is a work that started with the master work of Alexander, and then Luciano added the minimal project, and now he's a postdoc at Maryland University, but he also is collaborating with this line of research. So I will make an introduction for who is not familiarized, and to put the work into a background. As you know, or you imagine, a thermal rectifier, also called a thermal diode, is a system that conducts heat, but has a preferential direction. So if you exchange the thermal sources or the system, heat will flow, but the current can be smaller in one of the directions. Represented in terms of the difference of temperature, this is the plot we get. And of course, what one tries to do is to get the maximal rectification factor. So just to put in context, there are in the last decades several experimental realizations of the thermal rectifier. Here is just to illustrate a case where it's a solid state thermal rectifier, which is made with carbon nanotubes, and some material is deposited to create an asymmetry so that there is a difference in heat conduction. But there are also other realizations with the optical traps, for instance. And in general, what we need to appear this rectification effect is that the conductivity must be an asymmetric function of the temperatures. This is what is necessary to have rectification and asymmetry. And in terms of modeling how this has been studied theoretically, I just want to summarize some of the most commonly used models. In general, there are chains, one-dimensional systems, where there are some kind of asymmetry that can be introduced, for instance, but taking two different segments or more segments, where in each segment there are identical particles, all interacting linearly or non-linearly, and there is also some kind of on-site or pinning potential that pins the particles to the lattice. And at the ends, two baths, there are different models, for instance, Langevin thermostats, Nose-Huber, just the scaling temperatures, different models have been used. We will use Langevin baths in particular. So these are the kind of systems we can call two-segment. And there are also other class that we can call graded systems, in which each particle or sets of particles have parameters that change gradually instead of being two or more separate segments. And in the quantum, there are also quantum mechanics models where also spin chains like Heisenberg or Ising chains are the most common. But what I am going to show you is related to classical point of view. So just to illustrate some kind of results obtaining with this modeling, these are moreover the first in studying this kind of change where one gets the effect I have shown to you before in a pictorial way, where there is the difference of temperature and the current, and barring in that case the average temperature, one gets these curves where in some cases there is a higher rectification. And what our purpose is to try to understand this analytically, why these different behaviors may happen. Here is the current in absolute value as a function of the parameter ruling the interaction between two segments. In this case, is a two-segment system. And when the interaction is too strong, the currents will tend to be equal. But when these interactions tends to decrease, then we observe that there is a relation between the currents that is maintained and is the highest possible. But there are some problems because we see here that when the interaction is strong, the currents are equal, so rectification vanishes. When this parameter is small, of course, if it is zero, the segments are not connected and there is no current. But we see here that there is a factor that stays constant. But when in this direction, we observe an increase of rectification, the currents are very small. This is a problem in yes. Yes, thank you. Here is the absolute value, but of course this is the smallest current, and the black is the highest current. So there is a difference of more or less 2 decades between them, as you can see. So, well, but this is another commonly observed feature that we want to understand. In this case, the model is here there are harmonic interactions, but the on-site potential is Frenkel-Kontorova, is cosinus kind of potential. So in this kind of theoretical works actually preceded this realization. Sometimes said it was found first in theory than in experiment, but of course, there is always a counterexample. And here we find very old work where they have seen the diode effect. Here is a summary of the production in this area. I have not checked it. I picked this extracted from this reference, where you see this is all in the in a whole century. And then from the 2000, there has been a growth. It seems that it's saturating. I don't know how it continues, but there has been a rapid growth. So the cases I have shown to you are more or less here, and the realization, experimental realization, started to happen in more quantity in this about 10 or at most 20 years ago. So this is the context, and most of this work, as I already mentioned, try, of course, to improve rectification, to understand theoretically how to improve rectification, and experimentally, of course, too. Given that there are problems, because sometimes one finds that rectification may be very high, but the currents produced are too small. So there is a constraint that must be taken into account, not just the rectification factor. So in this context, our motivation was to understand what I have shown, summarized some laws that appear the dependence on the temperatures, how it arises, the conditions, the requirements for rectification, which is the preferential direction. In some cases, it's not obvious in which direction the current will be higher. And in particular, the dependence of the conductivity on temperatures and other parameters of the system, scaling laws in particular. And to deal with this problem analytically, mathematically, of course, this is the reason we try to find a simple model, in the sense as much simple, tractable mathematically as possible. You can interrupt if there is some question is not clear. So the system we consider is rather is a two-particle system where each particle can be subject to an on-site potential, and there is, of course, an interaction between them. And here is the Hamiltonian of the unidimensional movement of the system, where we have the potentials, on-site potential for each particle and the interaction, and we, to make the system tractable, we consider the interactions as much linear as possible. So these are essentially all harmonic, but we introduced nonlinearity that, as we will see, is essential to obtain the diode effect in each one of the on-site potentials. Then I will show if there is time. Of course, we started to add the linearity only in this term, but there were mathematical limitations to obtain analytical results, so we passed to study this kind of system. Here, I already called the attention of this parameter epsilon, which will be treated as a perturbative parameter. So the nonlinearity is perturbative to be able to obtain analytical results. And well, here are the equations of motion where we added consider each one of the particles is in a thermal bus, Langevin thermal bus, okay? But we also used other bus to see if some of the obtained results, some critical results, would depend on the bus. There are some dependencies on the bus, and you used Nosser-Hoover thermostat too, but numerically. And the current is defined as usual as the energy transfer from one particle to the other. So starting from one of the sources to the coldest one. So just to tell you the conclusions, so you imagine what we can find. With this simple system, it is possible to observe the rectification effect, nonlinearity and asymmetry. And asymmetry, of course, is necessary in this kind of systems. Nonlinearity is necessary too. But with this system, we can see which is the role they play, how the diode effect arises from these conditions. Nonlinearity, because we are keeping all the parameters constant. We need some dependence on the temperature, and the dependence on the temperature can come from intrinsic dependence of the, for instance, stiffness and other parameters can depend on the temperature, but we keep, as is usually done in this kind of models, I described it to use the chains. Parameters are not temperature dependent intrinsically. We wanted to see if they are constant, how the dependence on the temperature arises. So this is the first condition, and the other is the asymmetry. It's not enough to have a conductivity that depends on the temperature. It must also have some asymmetry. And in this way, we obtain analytical expressions that allow us to understand and even to describe some of the laws and behaviors we observed for chains, qualitatively, of course, and other insights that we have not observed in chains. Yes. See, this definition of energy transfer. See, this the work made by one particle over the other, but this energy is provided by the heat bath. Sorry, this is well, is qualitatively is work. Actually, is work. The work accomplished by one particle over the other, but we can also look at the energy transfer from the bath to the first particle, or from the last to the coldest bath, and these results give the same. Okay, this is the flux of energy in the steady state. Of course, it's not in the steady state. The results are different, but we are looking in the steady state. This F, yes, this is the for the nonlinear part of the force. See, this is a standard definition used to study the heat. Yes. Yes, I tell you intuitively what can, yes, because maybe a discussion about heat or work, and we are measured work, but we interpret this transfer of energy as heat because it's the energy that flows from the hot to the coldest reservoir. Okay? But of course, the transfer of energy between particles is mechanical. Okay? Yes. Over realizations, many realizations. Okay, so I will, of course, not show you all the calculations, but I try to highlight some results. As I told you, the approach is perturbative, so we assume that this displacement from the equilibrium position can be expanded in a power series of the epsilon, which is the intensity of the nonlinear forces. And of course, the current also will result in a perturbative expansion where it will be calculated with these correlations. So look that this first term, if there is no forces are linear, epsilon is 0, and we will keep only this term that corresponds to a linear system. So to introduce the nonlinearity in the conductivity, we will need to calculate these and higher order correlations. Yes, it was defined above. So this is the definition we discussed. And if we now admit that each one of these displacements can be expanded in this way, it's just to substitute and separate the terms with different powers, okay? And well, of course, at 0 order, the system is linear. One can solve it, and just for a check of consistency, what we obtain is here explicit in the temperatures. Here is the coefficient will contribute to the current, and appear the temperature, but in these coefficients there is no temperature dependence. Of course, as expected. So without entering details, what we arrive is that the contribution at zero order, there is the difference of temperature, and this coefficient is time independent. So this shows that a linear system cannot introduce dependence on the temperatures in the conductivity. For any choice of the system parameters, then we cannot observe rectification. And at first order, we could go further, but already the first order will introduce the impact of the nonlinearity in the conductivity that we want to see. So here also we can solve in terms of the solution at the previous order, but there appears some function that I will show to you, and this is a function of the forces applied to the zero order solution that are the responsible for introduced temperature dependence. Okay. So this is the main conclusion, but of course we need temperature dependence, but it is not enough. We need also some kind of asymmetry. So as to summarize, the first order contribution to the current has this factor that depends on the temperatures. Before going on, we checked that this expansion works. So here is a comparison to illustrate the comparison between the analytical results and the simulation, the numerical integration of the equations of motion. I will not enter in details, just want to highlight the agreement between the approach, the analytical approach, for small enough values of the perturbation parameter. Of course, we don't expect to be valid further. But how the dependence on temperature is introduced, this is just a symbol. But if we look at the dependence, we see that it is given by this expression where there are essentially two terms, and this beta, sigma are all coefficients that do not depend on temperature. The dependence on temperature emerges from this G, that is a function of, this is the average temperature, and each term contributes with one of the temperatures. Just as illustration, I am showing the parameters sigma and beta for the simplest case where particles are identical. And we see that even in this simplest case, in this simple model, the dependence on the parameters is very intricate. In some cases, in the larger system, we cannot predict or scan all parameter space. There are many parameters, and this may give some hints to understand the dependence on model parameters. So this function is where the effect of the nonlinear forces come from. And well, of course, it comes from the calculation of the correlation. We have to add many terms, many pages of appendix to arrive to this example summarized here. If the force can be written as an expansion, the function G will have also an expansion where the coefficients are related to the coefficients of the expansion of the force, just to show how it comes from. In the cases we have studied that are power law potentials, then also the forces, we obtain this relation. Another case we studied to relate to Frenkel contour of a system where the on-site potential is cosinus. We also obtained results for the potential that is hyperbolic cosine 2. So these examples were obtained particularly to relate to the most used cases in the literature of chain. So we have, for instance, the Phi4 harmonic, all can be related to this class. And the main difference is that these are not confining. This is not bounded. These are unbounded, and the Frenkel-Kontorova is not bounded. So it may present different characteristics that are reflected in this function G. When use a high temperature, the profile will become irrelevant. So this will give some properties that we can understand with the form that G adopts. So to summarize, we see how nonlinearity introduced temperature dependence through this function G, and this is general enough. No? The other parameters will enter in the coefficients. Yes. See, I will show soon. Well, let me see. Okay, no, it's not here. So as I already said, temperature dependence is necessary, but there must be an asymmetry to produce the rectification. And of course, in the linear part, we have nothing. And in this K1 is that we must have the asymmetry. The asymmetry will be introduced by this argument of the functions, the function G, through all the model parameters. Just to define the rectification, there are many forms. Basically, we pick the difference of absolute temperatures over the average in this case, and you see that what remains is proportional to epsilon. So the rectification in this system is very small. It's perturbative. It's proportional to the perturbative parameter epsilon, but we are not looking for a large rectification, but to understand the dependencies. And now the examples I will give is just to see how to get the difference between the asymmetry. Well, one of the cases, wait for the figure come next, the easiest case is the symmetric chain, that is the case where both particles are identical, and the asymmetry must be introduced by the on-site potentials. So just for you to see a case, here is the rectification that is proportional to the difference of case as a function of the interaction parameter. Here, to simplify, one of the on-sites is 0, and the other is something. In this case, is the either or Phi4 or cosine, and we observe the decay of rectification with Ki, as I shown in the experiment by Casati, where the numerical experiment by Casati, where increasing the interaction between the two segments, one obtains a decrease of the efficiency, and in the limit of 0 Ki, not strictly 0, but in the limit is relevant, gives maximal or near maximal rectification as observed in the chains. So the small Ki, remember that Ki is the stiffness of the interaction between the particles, is relevant, the limit of a small Ki, so we simplify the expression studying that limit. That is the limit that is usually studied in the numerical in the systems because it's which provides the largest rectification. So in this limit, in this case, I will show a case where the on-site nonlinearities are the same. In the previous, the particles were identical and the on-site nonlinearities were different. Here, we consider the same nonlinearity and different parameters. We observe, I will show you directly the plot, changing, oh, sorry, it's inverted the figure here. So we keep all equal except, for instance, the masses or the constant of on-site interaction of each particle, or the coupling, even the coupling to the bus. And in all cases, we observe rectification increasing with temperature with a law, where we are not, of course, the difference of temperatures will increase, but which is the concavity, it depends on the potentials. And I'm not comparing in parallel, but in the cases where the Frenkel-Kontorova or the Phi4 model are used, this dependence of the rectification with the difference of temperature is characterized by certain law or concavity, and it is reproduced by this simple model. Also, we studied for instance, the asymmetry parameter, that is the coefficient. If we are taking only the masses asymmetric, this is the quotient between them. And of course, if they are equal, as everything else is equal, if they are equal, the rectification will be 0. But outside that case, we can see when rectification is maximal. This is for the Phi4. And also here is another example that is for the related to the cosine potential. One is 0 and the other on-site potential is cosine. It is essentially Frenkel-Kontorova. And we, for instance, obtain the dependence of the rectification with temperature, with presents a maximal behavior. And again, this concavity is characteristic of the Frenkel in chains. Let me see. You see here is subtle, but in this case it's not Frenkel, and we get straight lines, for instance. For other potentials, the concavity may be inverted. So I don't know how much time there is left. Ah, okay. So this is not final remarks, but the remarks of this part. Just to summarize, we obtained analytical results, starting from a very simple model, two-particle system, and we can obtain analytical closed form expressions for the temperature dependence of the conductivity and the how it emerges from nonlinearity, and how the asymmetry can, of course, we must choose certain difference between the parts of the system, or even, as we have seen, with the coupling to the bus. Even when the two parts are identical, but the coupling to the bus are different, this predicts a rectification factor, which was not known in previous literature. So the preferential direction can also be predicted depending on which is the on-site potential, for instance. In some cases, in numerical simulations of chains, one observes inversion of the preferential current, which remains unexplained. And here, we, with a closed expression, we can see how this can occur. In the minutes that rest, I want to tell another part. Actually, this was the first part, because as I told before, we have thought in small systems and just to put the nonlinearity in the interaction, to put some kind of non-harmonic potential that can range from here is not the expression well, but 2 is the harmonic, can be subharmonic, or even take the limit of the exponent to infinity that will give a square well. And but we didn't manage to obtain analytical expressions in that case, nor perturbative, because we will need to obtain more terms to obtain a diode effect. But what I will be brief to show you the main results we obtained. This is not analytical, it was only by integration of the equations of motion. Here I put short chains because in some cases we used one particle at each side, but we also verified that the qualitative results remain when the number of particles increases. I haven't said that, but in most of these models, increasing the number of particles will make the rectification effect decay. So this is the form of the interfacial potential. And what we got is we were interested in the dependence of the rectification with this exponent. And what we observed is that for enough low temperatures, here are the two currents, here J is defined in absolute value. And of course, there is one, you can see, I don't know in which direction each is one in this case. But we observe that there are more or less 3 decades quotient between the currents. And if we measure the rectification, it will be nearly maximal when we tend to the limit of the square well in that case. So this happens for enough low temperature. This is what we call it approaching the perfect diode, not perfect in the sense that one of the temperatures is strictly 0. It's very small, much smaller than in the other direction. But the rectification takes nearly a maximal value. And since this limit is interesting, we have done simulations only for the square well, and also relating the currents. Here the bars are the count of collisions with the walls, and that is the potential. The walls means that the difference takes the extreme values, and of course the currents are related to the collisions with the walls. There is also dependence on the width of the potential well. And well, here is the plot in terms of the difference of temperature. Well, this seems nearly 0, but as we have seen in the log scale, it is not strictly 0, but is much smaller. And at high temperatures, this is destroyed. We see here that the currents are nearly similar. The rectification only has a maximal value for some finite value of the parameter mu. Here, we can see this is 2, so it's a bit larger than 2, but in other cases, depending on the rest of the parameters, it can be smaller than 2, the exponent for which the rectification is maximal. And this was done for the simplest case, where the on-site potential is harmonic. So the only nonlinearity is in the interface, in the interfacial potential between 2 or chains of particles. This examples are for, I think that 2 or 4 particles, 2 particles, but we observed that for chains also we observe this effect of maximal rectification in the limit of the exponent mu to infinity, and this is not valid for large temperatures. And we also consider other on-site potentials, Phi4, Frenkel-Kotorova, that are those usually considered in the literature in this kind of numerical experiments. And in all cases, we observe that here is the temperature. For low temperature, the rectification, which is what is plotted here, it tends to maximal values. Of course, Frenkel-Kotorova has a more rich topology because it is not confining. The Frenkel-Kotorova will tend to be the harmonic for low temperatures, and for high temperatures, the profile will be irrelevant, so we'll tend to the linear case and the rectification will vanish. Well, I think that this is basically what I wanted to tell you. In this other part of the work, we put only at first the interface nonlinear, but then we also introduced other nonlinearities, but the features I highlighted are also present beyond the harmonic case. And as the main observation is that at high temperature rectification, there is a finite value of mu for optimal rectification that will depend on the potentials and other model parameters, while at low temperature, the square well is the optimal case. And we also observed that the preferential direction can be changed by changing the exponent, mu, for instance. Well, these are the main observations. The first part was published about 1 year ago, about a bit more than 1 year, and this is now finished but submitted yet. So as perspectives, I would say, well, I have not abandoned the idea that the nonlinear interface, only nonlinear interface is tractable in some way that we must still think. And the results we obtained perhaps can be in some way used to analyze the problem for the perspective of overlapping phonon bands. Just an idea, of course, to illustrate the case of one particle. Here's one particle where there is nonlinearity, and we can obtain the spectrum of the particle. In the case of the particle, the spectrum will be, the width of the spectrum will be given by the realization of the stochastic noise. But one of the things is interesting is that the nonlinearity will introduce dependence on the temperature, and for instance, the stiffness will be temperature dependent. In some cases, the diode effect is produced by putting at hand the dependence on the temperature of the parameters on temperature. And here we can see a way to obtain the correspondence, effective temperature dependence, looking at the conductivity, for instance. So I think this is all I wanted to tell.
There are questions?
Thank you very much for your presentation. Like, I have a curiosity, like, did you try to see what happens in the limit of high viscosity in which you can work Yeah, like you can neglect inertia
Sí.
terms and work with
Yes,
first order differential equations.
overdamped.
Yeah, in
Yes.
the overdamped. Because
We have not done that, but we observed that it seems that in the overdamped limit that we discovered by analyzing the model, the rectification can be higher.
because I
So-
guess that these are models that are even easy, well,
Yes,
that are
yes.
easier to analyze. No?
Yes, yes.
Thank you.
You have obtained explicit equation and formulas, but I missed the intuition. Why is there this rectification? Why is different putting a temperature in one side and in the other when you have a nonlinear potential? Is there any intuitive way to understand this?
Intuitively,
Yeah.
you mean? Which is the rectification direction?
Why
the
do you have a
preferential
difference in direction when you have a
of-
potential which is symmetric but nonlinear?
Really, I don't.
It's always the
Well, why? If you mean if I can predict which will be the preferential direction,
Sorry.
yeah, there are some rules that we get a posteriori, but it's not very intuitive, I think, because sometimes depends on the temperatures, the difference of temperatures, for instance. So.
Just a curiosity, you mentioned there is a raise of an increase of attention to this problem. Are there practical applications for this, or is it something useful?
Well,
I don't know.
Well, there is some search in this direction, but I think that the efficiency is not high, it's very low. Yes, that is true. But there is an enthusiasm in trying to improve efficiency.
The materials used, when you mentioned experiments, are always a semiconductor, right?
Yes. Yes.
Is it possible to do it with, I mean, because the conductivity must be, it's probably low. So you put something like, you put a metal, something like that, which is a very high conductivity. Do you think it would be possible to maybe put something?
Really, I don't know. I don't want to speculate. I'm not sure.
Maybe we would, engineering, putting some periodicities or changing materials or things like that, like one does in.
Yes, I know how
with light or something like that. No? So this is with the
yes, I will think that certainly this is important, but I don't have an answer.
I was going to ask. Well, I mean, you have many different mechanisms. Okay, asymmetry in the potential, in the connectivity, in the experiments. Which one of those effects is the most relevant? Or you know, is the due to asymmetry in the parameters?
Well, the asymmetry, indeed, there must be an asymmetry.
You don't need it.
The asymmetry, yes, the material, or in some cases, in some optical realization, there is an intrinsic dependence on the temperature of the parameters depend on temperature. So in that case, you don't need nonlinearity, but the asymmetry you need always.
Questions? Okay. Natalia will stay here for a couple more days. When you have any questions, you can ask her. She's on the first floor. Okay, thank you.
Thanks. Thank you. Sí. Sí.
¿En qué régimen, o sea, qué suposiciones tuvieron? O sea, porque veo que los resultados finales que tienes solo dependen de la temperatura de los ángulos.
Sí.
O sea, pero en medio ahora tenemos una definición de la temperatura de las partículas, ¿no? ¿O no?
Se puede, no, se puede calcular como, bueno, en términos de energía cinética media.
Si tienes que estar de equilibrio,
de estado, no, equilibrio no, pero estado estacionario. Es estado